Okay, hello everyone, and welcome back to Qubit by Qubit. We are on week number 15 now of our Intro to Quantum Computing course. Welcome back. I hope that you enjoyed the lecture on Sunday and are really excited for our first lab talking about the IBM Quantum Experience. So we've spent, the last 14 weeks, all of semester one, the last bit of semester two, talking about the mathematical and some of the programming behind quantum mechanics, some of the math behind it, physics, all that kind of stuff. Now we're finally moving on to programming actual quantum computers. So today, for the first time, we will create a circuit, run it on an actual quantum computer, see what that looks like, and you all will get to play around with that as well in the coming week. So I hope this is really exciting. This is, in my mind, kind of the first, everything else before this has been the background for quantum computing. Now we actually get into running quantum computing, running quantum programs. Okay, so let's get right into things then, because today's lab is going to be a little bit different. I will explain that in a minute, but the general format is still the same. We will start off with our attendance quiz. We'll have, actually, we do have one question from last week. I guess that's not in here, but we do have questions from last week. Oh, sorry, that was right after. Sorry, pre-lab Zoom feedback, then the questions from last week, then the lab content, and post-lab Zoom feedback. Okay, so let's do the attendance quiz real quick. We are lab number 1. The passcode today is 8681, which is also in the bottom right of the slides. This week, you should actually see a question. So hopefully you don't see a blank one again. And the question is, which concept from semester 1 did you find the most challenging to understand? So again, just looking for some feedback on our part. As always, this quiz is not graded, but it does count for your lab attendance. So please be sure to fill it out. And let me know in the chat if you have any questions or concerns with doing that. Okay, so pre-lab Zoom feedback. So we have a quick reminder on the bottom here, just saying sort of what the content was this week. This week, we talked about the quantum circuit model, which we'll do a quick review of in the lab today as well. And we talked a bit about the comparison between classical circuits and quantum circuits. So I'll throw up a poll and just let me know, as usual, how you found this week's content on a scale of hard to very easy. And also, as usual, if you have any particular topics, I don't know, this week, like I said, is a bit different, but if any of these topics in particular confused you, please feel free to let me know in the chat, and I will try to make a note of it to either cover in the lab or possibly as part of the optional content at the end. Okay, so yeah, I'll give just another 15 seconds or so for everyone to vote. And then I'll go ahead and share the results. So one person direct messaged me, could we have a little time after the lab in this meeting to talk about teaming up for the Q hack? Sure. I guess that's a hackathon. Yeah, I think that's fine. So we'll do that after the lab, as mentioned. Okay, so I will go ahead and share the poll. There you go. So you can see most people are rating this 3, 4, 5, which is great to see, but we're still going to do a quick review. Okay. So one quick question from last week that I think I actually addressed, at least briefly, in this lab, but we're going to go over it again in a little bit more detail, just because the question did come up a fair bit. And the basic, question that was being asked is, how do you know the direction of rotation for the various rotation gates? So as a quick reminder, last week we talked about the Rx, Ry, and Rz gates, and we learned that those are the gates that rotate a vector on the Bloch sphere around the X, Y, or Z axes. Now, of course, there has to be some direction of rotation, right? Rotating by 45 degrees that way is not the same as rotating by 45 degrees that way. And so it turns out that the convention we use is that rotations are always counterclockwise if the angle is positive. So in other words, rotating positive 45 degrees means rotating counterclockwise 45 degrees. Rotating negative 45 degrees means rotating clockwise 45 degrees. Now, in order for this to make sense, you do need a perspective. So I've done this a couple of times when working with the block sphere, but you have to imagine looking at the block sphere as if the axis was pointing right at your face, right? So for example, if we're considering the Rx gate, we have our x-axis here. We're going to imagine that this axis is pointing at us. So our eye is here looking at the sphere like this. Okay, and so you can imagine the x-axis is coming like straight into your face. From that angle, counterclockwise is positive rotation. So if you just try to visualize what this would look like, counterclockwise, in this case, the 12 is kind of like up here. So then counterclockwise goes in that direction. And so that is a positive rotation around the x-axis. You can do the same thing with any of the other axes as well, as long as you just make sure you're visualizing as if the axis was pointing right into your face. Now, this explanation is exactly equivalent to something called the right-hand rule, which you may or may not be familiar with. If not, you can just remember what I said about counterclockwise axis into your face. But if you already know what the right-hand rule is, that also works for this explanation. Okay, just looking at comments. Can you help with information around future prospects in quantum computing for working professionals? Sure, we can talk about that at the end. I'll again make that the optional section. But yeah, for sure. The code for the lab is in the bottom right, as people are saying. Somebody direct messaged me saying they can't hear my voice. I'm going to direct message that person back because I'm assuming everybody else can hear my voice based on based on the comments. Okay, a few other questions. How do we orient ourselves around Z? Yep, good question. So Z is going to work the same way, but this time you have to imagine looking at the sphere from the top, right? So here we would be sort of like leaning over the sphere, looking straight down, so that the Z axis is pointing right into our face. And by the way, I don't know if I ever explicitly mentioned this, but this symbol that I keep drawing here is supposed to be an eye. I don't know how obvious that is, but it's supposed to be like an eyeball looking down at the Z axis. Or here, you know, looking toward the x-axis, that kind of thing. Okay, why are points on the sphere only measured on the surface and not inside the block sphere? So the short answer to that is that points on the surface are pure states. Points inside the sphere are mixed states. I had a little bit on that in the optional content from last week. By the way, the optional content from last week is pretty long. I think it went for, well, I don't remember exactly, but it went for like half an hour or so. In the lab recording on YouTube, there's like chapter markers. So you can just go into the description of the video, and one of the markers is called mixed states. That's where I talk about states inside the block sphere, if you're curious. It's not necessary though. It's not part of this course. Okay, so the x-axis positive direction is in the up direction. I guess, I mean, however you want to envision it, I think the most reliable way to remember rotation directions though is with counterclockwise and clockwise. So that's how I would recommend doing it. Okay, cool. Let's move on then. Let me just see, I don't think, yeah, there's nothing else I wanted to say on that. So let's get into this week's content, and I'll also just stop sharing this. Now, this week, like I said, is all about the IBM Quantum Experience, and so that's what we're going to be talking about. In the first half, I'll just go over some slides for the quantum experience, so high-level introduction, talk about some logistics for how we'll do it in these labs. And then for the second half, I'm going to switch over to my primary computer and go on IBM Quantum Experience, show you a couple of circuits, And then the part that's a little bit different about this lab is that all of the content here should not take us the full hour. Hopefully we'll have like 10 to 15 minutes at the end where you can just play around with the quantum experience and ask me questions if you can't figure out why certain things are the way they are. So it'll be a bit more unstructured at the end. Hopefully that's okay. It's a bit of a different format, but we'll give it a shot, just so that you all have a chance to play around with the quantum experience with other people sort of talking about and helping you out along the way. The optional content, which I will do after 1 hour has passed, so we will spend the full hour on the IBM Q experience. But after that, for the optional content, I will talk about noise and errors in quantum computation. This is going to be a high-level overview because noise and errors is like a major area of research. You could talk about this for days, but I'm just going to give a high-level introduction to some of the main concepts to do with noise and errors. All right. Let's move on then to IBM Q. So here's a diagram that I believe you saw in lecture this week that is a high-level overview of the quantum circuit model. So the quantum circuit model is, as it says, a model. It's a theory, and it's how we build quantum circuits in the IBM Quantum Experience and pretty much every other sort of quantum framework that I'm familiar with. The way it works is it has three main parts. You have your input. So somehow you need to tell the system, for each qubit, so I should point out, this is a 3-qubit system, right? We have qubit 1 up here, qubit 2, and qubit 3. Somehow you need to tell the system how you want each of those to be initialized, or how you want them to be created in the beginning. So here, all of our states are initialized to 0, and so every piece of our circuit is going to get 0 as the input. Next up, we have our gates, which we should be familiar with. We've seen this circuit notation before, and we just have these symbols that are associated with the matrices we already learned. So you'll see in the IBM Quantum Experience, for example, there is a thing called the H gate, and the H gate does exactly what you would expect. It's the Hadamard gate. We know how to write it as a matrix. We know that it creates a superposition, and all of that is going to look very similar in the quantum experience as well. These two over here are C-naught gates, or controlled X gates. This is just a shorthand notation. It's perfectly equivalent to write it as this as well, just with a dot and an X. But this is just a shorthand notation. We'll talk a bit more about what all of these do as sort of a refresher once we get into the IBM Quantum Experience. But basically, there's some gates in the middle. And then the final step of this model is measurement. So as we learned a couple of weeks ago now, measurement is not something we usually talk about in classical computing because it's very straightforward. If you have current on a wire, it always gets measured as 1. And if you don't, it always gets measured as 0. In quantum computing, though, the measurement is complicated, right? And we learned about measuring on the z-axis, the x-axis, what the difference is, how superpositions collapse, all that kind of stuff is in this final step of the model. Can't see what you're writing. Oh, can other people see this? Yes, okay. Oh, some people say no. Interesting. Okay, I am not sure what's going on there. Okay, majority are saying yes. Hi, yes, thank you. I'm not sure. It might just be a lag thing. Maybe it's not updating on your side, but. Okay, so reading just through a few of the questions, please explain the circuits and how they connect between each other with gates, then measurement. It was unclear in the lecture. Okay, I will try and do that. I think it'll work best once we get to the quantum experience, but I'll make sure to go through that slower. Implement Grover's algorithm, so I can mention it on my resume. We probably won't do Grover's this week, but I'm sure that later on in the course, we will have plenty enough knowledge to do Grover's algorithm. Okay, so let's move on. Now, like I said, this section is not super long, so I'm just going to do a high-level overview of the IBM Quantum Experience. I'll go back one more time for questions, and then we'll go onto the actual website itself. So a few just sort of high-level things. The IBM Quantum Experience is a cloud-based quantum computing platform. So what that means is you log onto it online, hopefully you all created accounts for the IBM Quantum Experience this past week. But it's just a website. You log on online, you build your quantum circuit, and then you send it off into the cloud. And IBM will run that on either a simulator or an actual quantum computer living somewhere in the world, right? Now, it offers a couple of different ways of constructing quantum circuits. You can either create quantum circuits visually, which is what we're going to do today. And you'll see it's just sort of a drag and drop interface where you can drag gates onto the circuit. Or you can also use code using Qiskit. So Qiskit is what we're going to start learning next week and what we're going to use for the majority of the course. But just for this week, we're going to use a more visual sort of beginner's introduction just to warm up before Qiskit next week. As I alluded to before, circuits can be run either on simulators, which you'll see are called QASM simulators, or on actual hardware. So all this means, well, actually, I'll talk about what this means in a second, but you'll see there are these two options on the actual website for whether you want to run on a simulator or run on hardware. And when you run a circuit, regardless of whether it's for a simulator or for hardware, your circuit is going to join a queue. And the whatever target you have, the simulator or the hardware, is going to work through all of the orders in the queue, and then it'll eventually get to yours. Okay, so let's expand a little bit on this point here, simulators versus hardware. The basic idea here is, as I said, there's two main ways that you can run your quantum circuit. One is going to be hardware. And when we say run it on hardware, we mean literally run it on a quantum computer, right? Set up all the qubits as individual atoms or whatever kind of system you're using, implement all the gates using laser pulses or something else, and do some kind of measurement at the output. So this is, like I said, you're running it on an actual quantum computer somewhere in the world and getting the results back. Usually, however, we will run things on a simulator first to sort of try them out. Now, what a simulator does, so a simulator is a classical computer, number one, and it sort of pretends to be a quantum computer. Now, that's really vague. What these actually do is they basically just do the linear algebra that we're already familiar with, right? So if you put together a circuit, the simulator will put together all of the matrices and vectors that are associated with that circuit, carry out all the math, and tell you what the answer should be, right? So like I said, what we usually use simulators for is to do sort of a check, right? Make sure that things are behaving as we expect them, probably on a smaller system, right? So we might try running our algorithm with 4 qubits on the simulator, make sure it works as expected before we try running it on like a 32 qubit quantum computer, right? Because running it on an actual quantum computer is more expensive because obviously we don't have very many quantum computers in the world right now. And so usually it's going to be faster and more efficient to test things on a simulator first. And that's what we're going to do today. Now, expanding a little bit on the last point of that slide where circuits go into a queue, you're already familiar with what a queue is. If you've ever been to a theme park waiting for a roller coaster or any other kind of line at a grocery store or whatever, then you know what a queue looks like, right? It's what we call first come, first serve basis. So if you are the first one into the line, you will be the first one to ride the roller coaster. If you're the 6th one into the line, you'll be the 6th one to ride the roller coaster. It works the same way with IBM's hardware and simulators. When you click the run button on IBM Q Experience, it will put your job into a queue, and then you have to wait for everybody else who wanted to do things before you to finish, and then eventually your circuit will be run. So a couple of logistical notes. So first up is on the difference between hardware and simulators. During the lab, so in particular today and also in the future, I will have you follow along with me for certain parts of the lab, right? I'll show you how to do a circuit. I'll ask you to do the circuit yourself and try running it. For those, we're going to ask you not to send the circuits to the actual quantum computers. In other words, don't send them to hardware. If you did, the queue would get too long. If however many hundred of us there are here, sent all of our circuits to the quantum computer at the same time, they would all take like a day to run, and none of us would get anything out of it. So instead, during these labs, I'm going to ask you to use the simulator, which, as I said before, you'll see is called the QASM simulator. That doesn't mean you can't run on hardware though. I just ask if you want to try running on hardware, please do it outside of the lab time so that we don't clog up the queues too much. Hope that makes sense. Okay, so this is where we're going to go ahead and log in. But before I do that, I'm just going to go and quickly answer any questions. Okay. So one person says, can we implement classical algorithms with quantum gates? The short answer to this is yes. I'm not going to go through the full formalism for why that is. But yeah, you can do classical algorithms with quantum gates. Okay. Anything else? Shor's algorithm. So all of these algorithms, like Grover's and Shor's algorithm, I'll write down a reminder to point you to some documentation on those if you do want to look into it sooner. But I think, like, for the time being, I'm not sure if we'll actually get to it later in this course, but I will point you to some docs just in case you want to take a look. Okay, so one person says, what is the difference between a quantum simulator and quantum hardware? The difference there is a quantum simulator is just a regular computer, right? It's like your laptop or your phone or whatever. It doesn't have anything quantum about it. It just knows how to do the math that we've been teaching you. And so that works for small systems, like a 4-qubit system. But if you tried to do the math that we were learning with a 32-qubit system, for example, the matrices and vectors would be so large that even a computer would have a lot of difficulty doing the matrix multiplication to actually solve those circuits. So a simulator is nice because it uses classical computers, and classical computers are relatively cheap compared to a quantum computer. But the downside is that it, of course, can't do everything a quantum computer can do. That's why we're interested in quantum computing in the first place. So a couple of people have messaged me saying because their bandwidth is low, they won't be able to join the quantum experience and the Zoom call at the same time. If that applies to you, I would recommend you stay on the Zoom call because I will be screen sharing the quantum experience. I'll be walking through everything as we go. So hopefully you still get an understanding of how to do everything. If you leave the Zoom call, then you won't be able to hear my explanations anymore. So please do stay on here. Follow along yourself if you can, but no worries if you can't. We have yet to learn how to program using Qiskit for a quantum computer. That's correct. So Qiskit is going to be next week. Okay, so somebody already tried IBM Q and it gave them weird results. I will hopefully cover that in my explanation. So one person asks, would classical algorithms run faster on quantum hardware? Not necessarily. And in fact, in most cases, no. In most cases, you actually have to work pretty hard to come up with an algorithm that is going to run faster on a quantum computer. Again, I'm not going to go into details on that, but that's the short answer. IBM Quantum Experience provides both a simulator and hardware. I'll show you how to toggle between those when we get there. Okay. Cool. So yeah, so I'll explain all the stuff with the quantum experience once we get there. One person just direct messaged me. They said, out of curiosity, what was the algorithm that proved quantum supremacy and how did it prove quantum supremacy? I can talk a little bit about that at the end of the lab as well. It's not one that's super common. Like it's not, nobody's done Shor's or Grover's algorithm at a significant scale. It was something called circuit sampling, and we can talk a bit about that at the end. Okay, cool. So I think I'm gonna stop there. I've been answering questions for a little while, and I'm gonna switch over to the quantum simulator. So just give me 1 second to do that. Okay, so hopefully everyone can see the IBM Quantum Experience on my screen. I will try and figure out how I check the chat. My goodness. Yeah, so just if somebody can give me a heads up that you can see my screen? Yes, I can see. Perfect. Thank you. Okay, so to start off, you go to quantumcomputing.ibm.com. So just type that into your browser. You should have to log in, and hopefully, again, you've already created an account. Once you log in, you'll see something like this. Now, if you haven't done anything before, you won't see any recent circuits, you won't see any latest results, anything like that. But this is the general interface you'll see, and I'm going to start walking through things from here. One person says, can I please zoom in a bit? Yes. Does that look better? Hopefully. All right. Cool. So once you are logged in and everything, the main tool that we are going to be using today is called the Circuit Composer. So here we're on our home page. You can see all of the different menu items on the left side here. We're on the home page. We want to go down to this one, the Circuit Composer. So as soon as I click that, you will see this screen open up. Now, there's a lot going on here, so I'm going to walk through what some of the elements of this screen are. The most important part here is the circuit itself. So this is where my mouse is right now. We have each of our qubits, qubit 0, qubit 1, qubit 2, and I can drag and drop gates from all of the different options up here onto our circuit. So for example, one gate we're familiar with is the Hadamard gate, the H gate. So I can simply just drag and drop that onto qubit 0. And now my circuit is going to start off with a Hadamard gate on qubit 0. I can drag it around onto other qubits. I can drag multiple gates on here, all that kind of stuff. To delete anything, you can just right click and delete to get rid of those elements. So that's the core of it, is sort of constructing the circuit elements there. Now, one big piece of, so that's, I guess, the gate part, right? If we think back to our circuit model, we have the gates in the middle. This is how you do that. I guess I'll mention now, there's a lot more gates up here than we have learned, right? So for example, we've learned the H gate. This little plus here is just another name for the X gate. So we've learned that too. This is the C0 gate, which we've mentioned a couple of times. We've also mentioned the T and S gates. We've mentioned a Z gate. Some of these we've mentioned, but maybe not explained in a lot of detail. And then there's some here that we've just never gone over at all. That's okay. You don't have to use all of them. Just use the ones that you are familiar with. Okay, so that's the quantum gates. Now, as for the states, the initialization, here we have 3 qubits to start off with. You can get rid of them by just hitting this little trash icon, if it would work for me. There we go. So I can go down to 2 qubits, or if we just want to do a 1 qubit experiment, we can do that. And if I want to add them back, it's just the plus sign there. So we can select however many qubits we want to run with, just using those controls. By default, all of the qubits are initialized to ket 0. Okay, so you don't have to worry about initializing them. All of these are already going to be set to ket 0. Some people are asking about the access code. Right. Let me just see if I can. Where is a good place to put it? Can I put it up here? Access code 8681. Okay, cool. Hopefully people see that, maybe, I don't know. All right. So coming back to things, yes, so qubit states are already all initialized to 0, so you don't have to worry about that. The final piece here then is measurement. And as we explained before, measurement is a little bit complicated in quantum computing. And so it's going to take me a second to explain how to read all of these diagrams. So let's go down to just 1 qubit for the time being, just because that'll be simpler to look at for now. Now there's 3 sort of areas you can look at the output. One is this little dial over here, which I will explain. One is the measurement probabilities down here, and one is the Q sphere over here. So there's kind of like 3 ways that you can visualize the measurement. So right now, we don't have a very exciting circuit. We just have all zeros. This is still saying 3 zeros for some reason. I don't know if that has to update or something. But anyway, maybe if I drag a gate, it'll update itself. So let's throw an H gate on here. Now, we know from just the linear algebra we've learned that if we apply an H gate to ket 0, it should create a superposition, right? It should give us a 50-50 superposition of Ket0 and Ket1. So let's see what that looks like. Okay, so you can see that all three of these elements, the dial, the graph, and the sphere, have all updated. So I'll explain a little bit about what all of them mean. The dial here shows actually a bunch of different things. The one that I'll point out, though, is just the amount that is shaded blue. So the amount that is shaded blue, as you can see here, it gives you a reminder, is the probability of being Ket1, which here we see is 50%. And so this is kind of a graphical representation. You know, when I did not have the H gate here, it was all gray. There was no blue, which meant no chance of being Ket1. As soon as I put the H gate here, now it's a 50-50 chance. So this is kind of the fastest way to just at a glance see the probability of being Ket0 or Ket1. Kind of a similar diagram is down here. So if we look at this graph, the measurement probability in percent is on the bottom, so 0 all the way up to 100%. And then the computational basis states, computational basis is just another name for the Z basis, which we know is Ket0 and Ket1. So here we can see there's a 50% chance of being in 0, 0, 50% chance of being in state 1. Now, the Q sphere is a little bit confusing because it is different from the block sphere. I just want to say that right off the bat. The Q sphere that is shown on this diagram is not the same thing as the block sphere. Now, in this case, you can see that Ket0 and Ket1 are on the top and the bottom of the sphere. This is equivalent to the block sphere. But as soon as you go to more than one qubit, it's no longer the same. So I'm not really going to talk more about the Q sphere. I'm mostly just going to ignore it. You're free to read more about what it means if you're interested. But for our purposes, we're just going to focus on the measurement probability graph and this little dial over here. Okay, so that's a quick overview of the states, the input, our gates, and measurement as the output. Does anybody have questions on just the basics I went over there? Okay, yeah, so somebody says, what's the difference between running on the simulator and the actual quantum computer? I will point that out. So let's actually go ahead and try and run this circuit. So we know that it should create a 50-50 superposition. And we also know that, you know, when we measure it, it won't measure as a superposition of Ket0 and Ket1. We should measure it as either Ket0 or Ket1, but with some probability, right? Okay, so to go ahead and run this, we're going to go up to the top right. And if you see right now, my screen says run on IBM Q Santiago. So Santiago is just one of the names for one of their quantum computers. We're going to go to run settings to change and run on the simulator instead. So here I'm going to go to system. And instead of Santiago, I'm going to scroll down until we find, here we go, the QASM simulator. Okay, so I'm going to select the simulator. We'll close that. I will come back and explain some of these settings in a minute. But for now, I'm just going to go ahead and click the big blue run button. Oh, right, circuit. Okay, I forgot about that. So one thing here, we haven't actually done a measurement yet, right? We've created our superposition. We need to actually measure. That is this little element right here. So usually in quantum computing, measurement is sort of pictured with a like a gauge, right? So this is kind of like the gas meter on a car or something like that, right? And you can see in the top right, it's telling us this is going to be a Z measurement. So again, the Z basis is Ket0 and Ket1. That is what we want. I'm going to go ahead, drag that here. Now, you will notice that all of our measurement visualizations updated again. And now we're no longer in a superposition, right? Now it's telling us that we have a 100% chance of being in the 0 state. Personally, I find this a little bit confusing. It's trying to tell you that after doing a measurement, you're no longer going to be in a superposition, right? And we know that. That's the collapse postulate. But showing that it's always going to be 0 is a little bit misleading. We know that in this case, we are sometimes going to get a 1 and sometimes going to get a 0. So I wouldn't pay too much attention to how these graphs change once you put in your measurement. Usually what I will do is I will go ahead, design my circuit, use all of these tools, And then the last step before I run it is I throw in my measurement. So we have our measurement, and then we're going to go ahead and run. So here you can see that the job was sent to the QASM simulator. So again, every time you run your circuit, it's thrown into a queue. So it'll go ahead into the queue, and eventually it'll get processed. To view the result, I'm going to go to the Jobs tab here. And you can see that this has already completed. Okay. So just looking at some of the questions, when you throw in the measurement, do you need to add 1 to every qubit? Not necessarily. I'm going to recommend that you do, though, just for now. You can, in quantum computing, measure only a subset of the qubits. We haven't really explained what that does, though, and so I won't talk about it here. Okay, so I saw quite a few messages coming by. So let me see. Yeah, so the Q sphere, I'm not going to talk too much more about. Maybe I can throw that in the optional section if people are interested. I'll spend a bit more time talking about it. When I add an H gate, I get 100% probability for just one. That is interesting. I think, like, if you follow along with everything I'm doing, you should be seeing the same results. If not, that would be interesting to look at. And I think the answer there would be to post on Piazza. Like, you can just grab some screen captures of what you're seeing, and hopefully we can help you figure out what's going on there. Do you need to talk about the measurement gate? Yeah, I think people were catching my error before I made the mistake. Okay, so yeah, I'm going to make a note. Maybe during the optional section, I'll just talk a bit more about all of these visualizations, because some people are asking about what the dial means as well. Again, I won't talk about that in detail right now, but I'll go into it in the optional content. Okay, code. Okay. Okay. I'm just trying to see if there's any other sort of like questions about the basics, I suppose. Yeah, so somebody's just asking, what exactly did we do in this circuit? So here, all we've done is we started off with ket 0, we apply a Hadamard gate, and then we measure the result in the Z basis. So again, measuring in the Z basis, you can think of it as being like a Stern-Gerlach Z experiment, right? So it's either going to end up as ket 0 or as ket 1. Okay. So I am going to just continue with the demo here. So once I have run this, remember, you'll probably open up in the docs view first. So you'll just want to switch over to the Jobs tab. And here you can see all of your results. So I have gone ahead and run this. The simulator already completed. So to actually see these results, I'm going to go ahead and click this. Okay, so now this is a results page. There's a whole bunch of data here about how many circuits you had when you ran this. You can see it even gives you a breakdown of the time. So here, transpiling and validating is kind of just like pre-processing. So this is like, I think we talked about this in the previous lab, but it's kind of like compiling your code into instructions for the quantum computer, or in this case, the simulator. You can see then we spent about 1/5 of a second in the queue. So the queue was really short. And then the simulator only took 2 milliseconds to run this thing. So really, really fast because it's a small circuit. Okay, so if I scroll down to the very bottom here, we will find our result. Now here, what we're looking at is basically the probability of being in the 0 state or the 1 state. The way that the simulator determines this is it runs the exact same circuit multiple times. So it repeats the same experiment multiple times. That in quantum computing is called shots. So here you can see in our run details, it's telling us it ran 1,024 shots. That means that it ran the circuit. So it initialized ket 0, applied a Hadamard gate, measured it. It did that process 1,024 times. And what it's telling us down here is the proportion of those times that resulted in 0 and the proportion that resulted in 1. And as we can see, it's about 50-50, right? If we ran it for, actually, it's quite close to 50-50. If we ran it for even more shots, so if we went to like 10,000 shots, these would keep getting closer and closer to 50-50. It's kind of the same as like if you flip a coin once, right? It'll either be heads or tails. If you flip a coin 1,000 times, it's going to get closer to 50-50 heads and tails. It's kind of the same idea here. Now, if I scroll down a little bit more, you can see the circuit that we did. So it saves this for us. We had our qubit, Hadamard gate, and then a measurement. The transpiled circuit is what was created for the hardware. So in this case, a simulator can simulate any gate we put on it, right? So Hadamard gate, measurement, no problem. It can simulate all of these things. But if we went ahead and ran this on an actual quantum computer, it might be the case that the quantum computer can't actually directly do an H gate, for example, right? Maybe it has all of these different lasers available on it, but no one laser actually does an H gate. Instead, it's going to translate your H gate to some combination of other gates. And so if that translation happened, you would see it over here. Okay, so let me see if there's anything else I wanted to go over. I think that was it. So again, just a quick reminder, you construct your circuit. First of all, you don't add the measurement gate and you observe superposition using the dial and the measurement probabilities. Then you add your measurement, you run on the simulator. And by the way, to change the simulator, you go to run settings and change the system. And also here you can see you can change the shots as well. So if you wanted to do for up to 8,000 shots, for example, you can do that. By the way, I'm not really sure what this job limit is. I think it might be for running on hardware only. So as long as you're running on the simulator, don't worry about using up your 5 jobs remaining. As far as I'm aware, you can just run as many simulations as you want. So once we did all of that, we hit run on the simulator. And in our jobs tab, we waited until we got a completed job. You click that, and then you can see the results of your simulation. So here we saw our 50-50. Okay, so I'm going to do one more example just to kind of show this whole process over again one more time. So going back to edit my circuit, I'm going to remove my measurement so we can see our superposition again. And now I'm going to try and create something called a Bell state. So a Bell state is entangled. And what it looks like, if you sort of write it down, it's going to be a 2-qubit state. It's ket 00 plus ket 11. So the interesting thing about this is that we should never get 0, 1 or 1, 0 as our results. Now, to construct this gate, it's pretty straightforward. Well, I need to add a second qubit first. We keep our H gate, and then we're going to add a C0 gate between Q0 and Q1. Now, again, our visualizations have updated. So here you can see that both of our qubits still have a 50-50 chance of being 0 or 1, which makes sense. If we look at our measurement probabilities, though, now it's telling us that the only possibilities are 0, 0 or 1, 1, right? And both of them have a 50-50 chance of occurring. Okay, so I'll throw in our measurements, one for each qubit, as I mentioned. Okay, now once we have those measurements, I will go ahead and click run again. So here you can see that this job is pending. So you can see the state is validating. Now it's run, so I can go ahead and click it. Okay, so let's go down and see what happened here. So again, we get a very similar looking result, except now we're looking at 0, 0 and 1, 1. Instead of just a simple 1-qubit superposition, we now have an entangled state. And again, we can go down and look at the circuit diagrams if we wanted to. Okay, so I want to show one more thing before I give some time for everybody else to play around with this. And that is a job that I ran earlier on an actual quantum computer. So just to sort of show you exactly how I would have done this, I would have gone to run settings, gone to system, and then I could select one of the actual quantum computers. So For example, here you can see IBM Q Santiago is a 5-qubit device. That's what the 5Q means. You can see it's online, which just means it's active. And there's 42 other circuits that are waiting before ours is going to get executed. So I ran this exact circuit this morning. It took about an hour in the queue. So just to stress this point, the fact that it takes an hour, that's not because the actual quantum computer is taking an hour to execute such a simple circuit. It's because there's so many other things in front of us that have to be executed first. So we have to wait our turn, essentially. So I would have selected this computer, IBM Santiago, and then you just click run, and it works in the same way. So it's really easy to switch between an actual computer and the simulator. I should also mention, you don't have to use Santiago. You can use any of the other ones. There is one of them called RMonk, which is a 1-qubit device. So this one tends to go a lot faster. You can see the queue is quite a bit shorter. So if you do want to just try running on an actual quantum computer, a 1-qubit circuit, you can do that with RMonk, and it should go a little bit faster. Okay, so I'm going to go ahead and show that previous run. So here you can see I ran it on IBM Q Santiago about an hour ago. And so I will click that to open it up. Okay, so let's take a look at the results here. The first thing you'll probably notice is that this does not look the same as the simulator, right? The simulator had only 0, 0, and 1, 1, and it had roughly a 50% chance on each of them. The first observation here is that we're quite a bit off from 50-50, right? We're 5% over here and 7.5% under over here. That's not because our circuit is wrong. Our circuit was the exact same, and it does exactly what we expect. But the numbers that you're seeing here, and the fact that you sometimes see these states, which we should never see, is just due to experimental error, right? This is because this was actually run on a real quantum computer, and on a real device, there's going to be imperfections, right? And we'll talk a little bit about that in the optional content today. The last thing I want to point out is the circuit diagrams, because again, you'll notice these look a little bit different. So my original circuit is the exact same, right? The Hadamard followed by a CNOT, followed by 2 measurements. But this is what was actually run on the real quantum computer. So first difference is that I used a 5-qubit quantum computer. So you can see that there's 5 qubits, but we just don't do anything to the last 3. But you'll also see that it broke our Hadamard gate into an RZ, a square root X, and another RZ gate. Now, again, that's just because the quantum computer, this IBM Q Santiago that we ran it on, doesn't have an H gate laser on it, right? Instead, it has a number of other lasers, and the IBM Quantum Experience has compiled our circuit down to something that this computer can actually run. So in reality, it would have had these 3 gates, but it should have, in theory, the same effect as our H gate. Okay, so that is a quick introduction to the circuit composer. As I said, I don't have any other prepared content, I guess. So I'll spend some time going through the questions, but for everybody listening right now, feel free, and actually, if you can, feel free to play around with the circuit simulator, try building, the 1-qubit superposition, running it on the simulator, try building this entangled state, run it on the simulator, and I will go through and answer some of the questions in the chat. Okay, so yeah, so one person says the H gate is supposed to make a pure superposition, but now it's showing just 0. So my best guess for why that is if you have a measurement, right? So I'm going to go ahead and just remove everything here, get back to our 1-qubit superposition. So notice here, I just have the Hadamard gate. There's no measurement, and I get my superposition. As soon as I add in a measurement, it's going to tell me that the state has collapsed, right? And yours might not say 0 here. Yours might say 1. It doesn't matter. But just keep in mind that's only because you've added this measurement. So I recommend always create your circuit without measurements first, so you can see what the superpositions are. And then only when you're about to run it, do you go ahead and add the measurements. Okay, so yeah, I talked about how to check the results. Yeah, so one person is asking about measuring along other axes. Indeed, what you're seeing here is that IBM Q only allows you to measure along the z-axis. There are ways around that, right? So one way, for example, is if you wanted to measure along the x-axis, you can, well, this is not necessary, so don't worry if you don't understand, but you can rotate your whole block sphere, so you can apply a rotation gate so that the x-axis turns into the z-axis, right? So in this case, that would be an ry rotation. Once you do that, then you can go ahead and measure in the z basis, and it will be equivalent to if you had just measured in the x-axis in the first place. Okay, so one person says, would running it for multiple shots have any meaning practically for a simulator? I understand it if we run against quantum hardware. Yeah, that's a great question. So even on the simulator, it does have a meaning because the simulator is going to run a random simulation of each of those outcomes. So when I said before that the simulator will sort of do the math to figure out what the probabilities should be, it'll do that, right? And so it'll figure out in this case, for example, that you're supposed to have a 50-50 probability of being in ket 0 or ket 1. But after that, it will essentially flip a coin 1,024 times to figure out what the results should be. And that's why even when we ran on the simulator, if I just go back to that one for a second, we still saw that these numbers weren't exactly 50%, right? And that's because even the simulator is going to try and simulate some quantum randomness. Now, to those of you who are asking what the seed is, if I go back to my circuit composer, you might have noticed this thing up at the top here, simulator seed. Now, this is essentially a number that the simulator is going to use to try and create some randomness. I won't go into more about exactly how that works. That's more of a computer science topic. But suffice it to say that this number up here is going to be used to generate some artificial randomness to make it kind of look more realistic on the simulator. So one person asked how to run with 100,000 shots. You can't. You can only go up to 8,192. You could probably do more shots if you decided to pay IBM, but at least the free version only has 8,192. So one person asked why in that result I just showed, it wasn't exactly 50%. And again, the reason there is because the simulator is going to create some artificial randomness, right? It'll figure out the exact probabilities at first, but then it'll flip a coin 1,024 times to figure out what your results should be. And when you flip a coin 1,024 times, chances are you're not going to get exactly 50% heads and 50% tails. Okay, so a few people asked about the transpiled circuit. I hope I answered that when I showed you the run from the real quantum computer. Yeah, in mine, the Q sphere is showing opposite results. So again, if you have a measurement on the circuit, I would say don't pay too much attention to these measurement symbols. They might look different from what I have. I would just recommend always designing without the measurement. It's okay if you put the measurement here and these are opposite or just totally different to what you see on my screen. That is okay. Yeah, so somebody's just asking what types of people can have access to the quantum computers with more than 5 qubits. Again, that would be a paid option, right? So all of the stuff that we're seeing here and that we'll do in this course, you can do for free on the IBM Quantum Experience. If you wanted to run experiments with 32 qubits, for example, or more, I think for those you would have to pay. Okay, so somebody's asking, what is the 32QV? That is a great question. This is, again, something that is not, well, actually, you know, I'll explain that as well in the optional content, because it's definitely not part of the course material. Yeah, so somebody asks about writing the whole circuit in programming languages. We can use Qiskit for that, and we will be teaching you that next week, which is why we started off with some Python. How to increase the number of shots, you can just change it up here in the run settings. So I could go, if I wanted more shots, you can just change this number. I could type in, a lot more shots, for example. Any of that is fine. Will there be revision of the gates like C naught? Yes, yeah, that's a great point. Actually, why don't I do that right now? Just reviewing how this circuit works. So let me go ahead and construct the entanglement circuit again. So that was an H gate with a C naught and then 2 measurements. Oh, actually, I'll leave off the measurements for now. So I'm going to switch back to my tablet and we will quickly review how this circuit works, because I think that would be useful. So I should mention as well, like the thing is with all of quantum computing, basically the way you usually do things is you design your circuit using math, right? You actually work through some of these calculations to figure out what gates you want to put on the circuit. And so that's part of the reason why we were teaching you all of the math beforehand. Okay, so I will stop sharing my screen here and we'll quickly go over the same example on my tablet. Okay. So hopefully everyone can see that screen change. Now, the circuit that we had there, as a reminder, was the following. Ket 0 in both qubits. Then we had an H gate. And then we had a control knot. I'll draw it like this. Okay, so I am going to sort of remind how this works just by showing what happens to each of the computational basis states when each of these gates acts on them. So first up, the Hadamard gate, we know it goes ket 0 into 1 over root 2, ket 0 plus ket 1. And then for ket 1, it's going to turn that into 1 over root 2. Whoa, that was weird. 1 over root 2, ket 0 minus ket 1, right? And so the only difference here is the plus and the minus sign. This is the H gate. Now for C naught is a 2-qubit gate. So I'll have to show you what happens to it for 0, 0, 0, 1, 1, 0, and 1, 1. So for 0, 0, it's going to stay the same. It's going to go to 0, 0. For 0, 1, it'll stay the same. For 1, 0, it'll go to 1, 1. And for 1, 1, it'll go to 1, 0. Now, the way to think about this intuitively, instead of just memorizing this pattern, a control NOT gate conditionally applies an X gate, right? So this is why we've kind of drawn it as like a dot with an X. Basically what this says is if this control qubit, we call the one with the dot on it the control qubit, if the control qubit is 0, don't apply the gate. If the control qubit is 1, then do apply the gate, right? So up here, we have our control equals 0. And so if you just look at what happens to the second qubit, it always stays the same. We don't apply our gate, right? Down here, though, in the second two states, we have our control as 1. And so, again, if you look at the second qubit, you'll see that we've applied an X gate, right? 0 became 1, and here 1 became 0, which is all the X gate does. And then the final piece here is the control qubit itself never changes. So if you look at all of the first qubit, it never changes when it goes through the C0 gate. So if I were to, well, actually, we're almost at the end of the lab here, but I'll just finish off this example. If I were to trace through this entire circuit, I might do it like this. So I know that we're starting off in the 0, 0 state, right? Now, the first gate in our circuit is an H gate. So I'm just going to say that. And now I know what an H gate should do. It turns my first qubit 0 into a superposition. So I'm going to get 1 over root 2, 0 plus 1. And then my second qubit doesn't change yet. Okay, now I can just use the distributive property here to expand this. So this is just equal to 1 over root 2, 0, 0, plus 1, 0. Right, so just distributing this multiplication across the addition, we get 1 over root 2, 0, 0, 1 over root 2, 1, 0. And then finally, we have to apply the C0 gate. Right, now for the C0 gate, we know what happens. We can just look it up down here. Our 0, 0 will become just 0, 0 again, so that's fine. Our 1, 0 will become 1, 1, so this is going to change. And so this is the final state that we expect. 50-50 chance of being 0, 0 or 1, 1. And indeed, that's what we saw on the IBM Q experience. Now, I should point out here, you could do all of this stuff using matrices, right? So you could write out the matrix for the Hadamard gate, you could write out the matrix for a C0 gate, and you could do all of the matrix multiplication. That's totally valid. But usually when you are considering circuits, you use this method where you sort of write out your state and then you do a transformation according to every gate that you're applying. So hopefully you followed that. Let me just see if there's any questions on that topic. Yeah, okay, so people were asking about C0 and how the circuit works, so I hope this helped. Okay, cool. So there's a lot more questions, which I'm going to keep going over. But for right now, I'm going to end off the required part of the lab. We are at our 1 hour mark. And so I'm going to use this opportunity to pop up. Oh, sorry, we have a key takeaway slide. I forgot about this. Okay, so just again, a quick summary of what we went over today. The IBM Quantum Experience is an online platform to run quantum circuits. So we saw an example of that. The circuit can be run either on a simulator or on an actual quantum computer. And once again, I would encourage you to actually try running a circuit on an actual quantum computer. It just might take a while because lots of people are trying to run things on the actual quantum computers. And then the final example that we saw is that combining an H and a C0 gate leads to a 2-qubit entangled state, which is that 0, 0 plus 1, 1 that we saw before. So a quick preview coming up next week, we are going to have Qiskit, like I said. So that is essentially doing all the same things that we saw here, adding gates to our circuit. But instead of doing it with a drag and drop interface, we're going to do it in Python using programming. Further resources are, of course, here as well. And then finally, we have our post-lab feedback. So I'll pop that up right now. Hopefully I helped clear some things up. I know that you have homework this week that involves the IBM Quantum Experience. So yeah, hopefully you have a better idea of how to do that. But as a reminder, I'm going to stay behind, spend some time answering questions to try and help some people out. Awesome. All right. Is this going to help with the homework? I hope so, yes. So hopefully when you go and look at the homework now, you should know how to use the quantum experience. We certainly would not have expected you to figure out everything on that website on your own. So as a reminder as well, this lab is recorded. So if you forget, how I constructed a circuit, if you forget how to look at results, if you forget how to get to the circuit composer in the first place, go ahead and watch this again. Everything was screen recorded. So you should be able to follow through step by step with what I'm doing. Okay. Cool. So I will go ahead and share the results from that poll in case you're curious. And then we will end off the required portion of the lab. So like I said, feel free to stay behind if you want to hear about any of the optional content or if you want to hear me answer questions. I am going to cap myself at spending 10 more minutes, I think, answering questions, and then I'll go into the optional content, just so I don't spend too long answering questions. Of course, if you still have questions after this, Piazza is always there as a resource. Okay, so if you want to head out, no problem. That's the end of the required content. I'll see you next week. If you want to stick behind, we have questions and optional content coming up. I'm just going to take a 30-second break to give my voice a rest, and then we'll get started. Okay, so one person direct messaged me a question, which I think is a good one. They just asked, does applying different gates mean shooting the atoms with lasers of different frequencies? So again, it depends on the type of hardware you're using, right? If your qubits are some kind of atoms, right, and your gates are lasers, then yes, that's exactly what it means. Different gates would be accomplished with different laser frequencies and different laser intensities, right? There are other types of quantum computers, though. And so for other types of quantum computers, there will be different ways of interacting with it. That's all part of figuring out what hardware you want to be running on. So for example, IBM Quantum Experience, when you run on any of their actual quantum computers, they use superconducting quantum computers, which use an entirely different set of actions for the gates, and they don't use atoms, for example, as the qubits. It works in a different way, which I won't get into. But yeah, it depends on the hardware is the short answer. Yeah, sorry. So the optional content today is going to be on noise and errors. And then I also made a couple of notes on some optional stuff to go back to toward the end of the lab. Okay, so somebody also asked, just for clarity, why don't we have errors in classical computers? That is a great question, and it's because of error correction. So we'll talk about that as well in the optional section. So somebody asks, by laser pulses, do I mean microwave pulses or something different? So yes, they can be microwave pulses. I say laser pulses generally, just because they don't necessarily have to be microwave specifically, but microwave pulses is one example, yes. So career prospects, I will come back to for optional content. Okay, so somebody direct messaged me. There was a strange result. Let me just take a second to read this. There was a strange result while exploring C0 with ket plus minus, applying C0 with control as the plus and target as the minus, changed the plus to minus and resulted in minus minus. Any explanation other than the math? Yeah. That is a great question. So let me switch back to the quantum experience screen. I'll also illustrate what the student is talking about as well. So one thing that you could try, right, is you could try creating different initial conditions on your circuit. So here, I believe their example was to create ket plus minus at the beginning, right? So I'm going to go ahead and create ket plus minus. So right now we have 0, 0. Now to create ket plus, I'm going to apply a Hadamard gate on the first qubit. To create ket minus, there's a couple of ways of doing this, but I'm going to flip my qubit 1 to be from 0 to 1, and then I'm going to apply a Hadamard on that, and we'll get a ket minus. Okay, so they created this state, and then they did a C0 on it. Oops. And then we observe what happens. Now, the interesting thing here is, well, I kind of need to talk about that, don't I? Yeah, okay. Well, maybe now would be a good time to talk about these dials then. So what I explained before was that the dials, the part that I explained before was that the amount that it's filled by blue is the chance that you're going to get ket 1 as your result, right? So here we can see both of our qubits are 50-50. But there is also a little black dial, right? This little black line here, it might be a little bit hard to see, but right now it's on the left of the circle. And when I started out, it was on the right of the circle. Now, that little black line there indicates the phase on the qubit. So what the phase is, that just means if you put like e to the I phi in front of your qubit, what would that phi be? Now, in this case, it's telling us that the phase is pi, which means e to the I pi is just -1. That means we're going to have a -1 in front of our state. Now, this is a little bit interesting because if you look again at what I did here, with my initial construction, we had a plus, right? +1. So all this is saying is you have your ket 0 plus ket 1. That sign in the middle there has a phase of 0 because it's just a plus. Here it has a phase of pi because it's going to be ket 0 minus ket 1, right? And so that's why we're constructing our ket plus ket minus state. Now, when I explained the CNOT gate before, I said that it does not change the first qubit, right? It only changes the second qubit. In contrast, what we see here is when I plop the CNOT on, it changes the first qubit, but not the second one, which is certainly very confusing. The short answer for this is that you just need to work through the math. And if you work through the math, you will see that changing this first qubit is equivalent to doing a change on the second qubit. It just so happens that this is how the quantum experience is showing it to us. So again, my best advice for sort of reasoning with these circuits is to actually try and work out the math yourself, right? Like sit down, figure out what all of the gates should be doing, figure out what your final state should be, and you should be able to reason about what you're seeing in the quantum experience as well. Okay, so let me go back to the chat. Okay, so let me find where I was here. Okay, so that was the strange result. This conversion of gate in the transpiled circuit. Yeah, okay, so somebody asked about adding noise in the transpiled circuit. So indeed, when we saw the H gate being transformed into 3 separate gates, that does add some noise to the system, right? Unfortunately, when you build a quantum computer, it might be very difficult to just directly do an H gate. It's an active area of research, but for right now, sort of the best we have is to transpile down to a circuit that we can do on a real quantum computer and just live with whatever errors that gives us. Okay. I'm skipping over some questions that are not as directly related to what we're talking about here. Again, not because they're bad questions. If I don't answer your question, I encourage you to just go and ask on Piazza. I just want to try and keep things in this lab somewhat focused on the IBM Quantum Experience. So somebody asked, isn't ket plus the same as ket 1? No, so those are 2 separate states. Ket plus is equal to an even superposition of ket 0 and ket 1. Okay. Is there a way to see the results on a block sphere in the IBM Quantum Experience? I don't think so. At least not that I'm aware of. Maybe somebody can point that out to me, but I'm not aware of a way to see the block sphere in the IBM Quantum Experience. Okay. Cool. So I think that I got through all of the questions that are, again, directly related to what we're talking about. So I'm going to go into some of the stuff that I said, I'll address after the lab is over. So the first thing I said was talking about these dials and the Q sphere. So I'll give a very quick overview. The little dials I already talked about, right? The blue shows you the probability of being in the state 1. The dial shows you the phase on your ket 1 state, right? So in this case, we see that the phase is pi. That means there's going to be a minus sign in front of our ket 1 state. Okay. Yeah, there is one other thing that you'll see on this is that sometimes the circles will shrink. That is a measure of entanglement. So if the circles shrink more, it means that the qubit is more entangled. If they're full sized, that means that there is no entanglement. I won't really get into how that is determined though. And just to show an example of that, just so you know what I'm talking about. See here, so with this entanglement circuit that I talked about, see how the circle on the inside got smaller? that shows us that this is an entangled state. But I won't really talk more about why that's important. Okay, so the only other thing I wanted to mention was the Q sphere then. The way that the Q sphere works is as follows. There's a couple of rules to it. The 0, 0, like the all 0 state is always going to be at the top. The all 1 state is always going to be at the bottom. Then if you kind of remember longitude and latitude from the block sphere, every different latitude is going to be a different number of ones. So for example, here we have 0 ones is at the very top, 2 ones is at the very bottom. The equator then is going to be all the states that have just 1, 1. So that would be the 0, 1 state and the 1, 0 state. So for example, if I just, I get rid of this and I create a full superposition. So this is going to be 25% chance of all the different values. You'll see on the Q sphere that it's showing an even probability of being in any of these 4 states. At the top, we have 0 ones. At the bottom, we have 1, 1. And then these 2 states in the middle have only 1, 1. Now, where it is sort of around the equator is not something I'll get into, but it basically just distinguishes between the different states that could have that number of ones. Hopefully that makes sense. So actually, I mean, I can't explain it. It's basically just, in this case, we have 2 states that fit on that level of latitude. And so we just evenly distribute them all the way around the circle. Now, one thing I will point out here, if you want to read more about the technical definitions of these things, and there are some details that I did not go over, if you go to the docs tab here, there's a lot of great stuff in here. Number one, there's a guided tour. So if you need a refresher on anything, want to hear it from someone other than me, you can do that. But you can also, there's some guides here. If you go to explore full documentation, there's a whole bunch of stuff here you can read in great detail about how the circuit composer works. Some of this is going to be beyond what we've talked about in the course. That's okay. You can read through it if you're curious. But the one that talks more about the Q sphere and the dials is right here under visualizations. So here, if you scroll down a little bit, you can see that it's talking about what the various things in the dial means. And then it also talks about how the Q sphere works with some more complicated circuitry. Again, not at all necessary. For our course, I would honestly just, you can always just use these measurement probabilities down here, right? And I would probably recommend that. But again, just if you're curious, you can look at the documentation for what those mean. Okay, so other stuff I said I would talk about. Grover's algorithm and Shor's algorithm, right? So I'm not going to try and explain those in this lab. That would probably be a full lab, at least, all on its own to explain how they work. But again, if you want to read more about that, I think, yeah, okay. So if you go to this explore full documentation again, and you scroll all the way down, there's a section all about learning quantum computing. And here you can see there's Grover's algorithm, the Deutsch-Joste algorithm, quantum phase estimation, and Shor's algorithm. So these pages are very comprehensive. You can go in here, it'll give you sort of an introduction to the problem, and then it'll lead you through all of the math, culminating in the actual circuit that you need to do, for example, Grover's search. Now, as you can see here, like this circuit looks very complicated. I agree, it's long. But if you look at the gates it's actually using, the only one that might be new here for us is the S gate, right? And so it'll teach you what the S gate does. But at the end of the day, this is just a much longer problem. It doesn't actually involve anything new or that you couldn't do. It would just take you some time to actually sort through how exactly the circuit works because it's just really long, right? So you can do that if you want, though. Okay, so I talked about the Q sphere, I talked about the dials, I talked about Grover's and Shor's. Oh yeah, teams for QHack. So I'm not sure who mentioned that originally, but if you do want to, I guess, like stay on afterward, I'll leave the call open for maybe like 5-10 minutes, and anybody who's interested and knows what QHack is, because I don't really, can maybe stay behind and form up with teams. So I'll do that toward the end. Okay. So somebody asked about career prospects in quantum computing. I'll talk briefly on that. Although I think there was a panel held at the beginning of semester 1. I don't know if it was recorded, where we got more perspectives on this as well. But at least in my opinion, quantum computing right now is pretty much where classical computing was in like the 40s, right? Like the 1940s. Okay, somebody says it was recorded. So I guess you can find it on Canvas, maybe. Actually, I'll do some digging and I'll attach a link to that in my follow-up email after this lab, assuming I can find it. But my quick answer is that quantum computing now is basically where classical computing was in the 1940s. And if you're not familiar with that, because I, for one, was not alive in the 1940s, basically what that looked like was classical computers were these massive machines that took up like an entire room or several rooms in a building. And they were specifically designed for solving, I think it was differential equations. I might be wrong on that, but there was one particular mathematical task that they could do really well, a little bit faster than the previously known techniques. And that was the original motivation for building these massive machines. And so today's code is 8681. Yeah, so going back to my explanation there, they built these huge machines just to solve one particular, small type of problem. And it wasn't until many years later that they started to sort of refine the technology. Computers became smaller. They figured out how to do more things with computers. And of course, here we are today when pretty much, everybody owns a smartphone or a computer or a cell phone or, some kind of digital device because of all of that early research. So quantum computers right now, same idea. They only work on very specific, very complicated problems, well, I shouldn't say they only work. They are only advantageous for very specific, very complicated problems. They're really large and bulky. We don't really know how to build them very well yet. They certainly aren't widespread. But over the next couple of decades, it's quite likely that we will get better at building quantum computers. They'll become smaller, they'll become cheaper. We'll figure out more things to do with them, right? Now, I'm not going to say that they're going to reach the same kind of widespread adoption of classical computers. I think a more likely end result is that they would kind of turn out to be like GPUs, right? So it would be what we call a coprocessor on a computer, which means it doesn't do the sort of primary tasks of sending email or running a PowerPoint presentation, but instead your computer will sort of delegate out certain particularly complicated tasks to the quantum computer to solve faster than your computer could do. And maybe one day, just like we can have computers that have GPUs in them, we might have computers with QPUs on them. Who knows? I think we're still quite a ways away from that. But yeah, that's sort of an overview. As far as careers though, a lot of the careers in quantum computing right now are still mostly research-based, right? So it would be around, okay, how do we do more interesting things with quantum computers? How do we build them for cheaper? How do we make them smaller? How do we make them, not have to be at millikelvin temperatures to operate? All that kind of stuff. It's mostly around the research. But I mean, literally just in the past 5 years, the number of industry jobs in quantum computing has exploded, right? Now there's like startups. It's not just at universities anymore. There's companies like IBM that are actively researching and investing in quantum computing. So we certainly seem to be experiencing quite a boom right now. We'll see where it goes in the future. I'm honestly not sure, and I don't think anybody is. So there's my quick spiel. Okay, so I also said I would talk briefly about the problem that proved quantum supremacy. It's something called circuit sampling. Now, I honestly don't, I kind of forget the details, and so I'm not going to try and explain it, just in case I make a mistake in saying how it works. But the part that I think is important to understand about the quantum supremacy experiment that was done by Google is that the problem they used was essentially an engineered problem that was designed to be as easy as possible for quantum computers while being as difficult as possible for classical computers. So essentially it was designed to tease out the difference between what a quantum computer can do and what a classical computer can do. My understanding is that the problem doesn't actually have any practical significance, right? So, okay, they ran it faster than any classical computer could do it, but nobody would actually care what the result is, right? So it was kind of just a show in that sense. Still a big deal, right? It proves that now we have quantum computers that can compete with classical computers in some types of problems. It's just at that point, the problems were kind of irrelevant and meaningless, right? Now, there was a second quantum supremacy experiment that didn't get as much hype because it wasn't Google. It was a team of researchers in China, I believe, and I don't know which lab or university they're with. But they showed quantum supremacy with something called boson sampling, which is actually a useful problem for simulation in physics. And so I know for a lot of people in the quantum computing world, that was in some ways even more exciting than Google's quantum supremacy experiment, because for the first time, it showed a useful result that a quantum computer could get faster than a classical computer. So if you are interested, you can look up what circuit sampling is. You can also look up boson sampling. Both of them are relatively complicated topics. I don't understand them fully, so I'm not going to try and explain them here. But if you are curious, you can look up some of those keywords. Okay, last thing I said I'd do before the optional content is quantum volume. So that was going back to the IBM Quantum Experience here. In the run settings, when I went to the different systems, we saw the name of the device. So for example, IBM Q Santiago, it has 5 qubits. But then the question is, what is this second number here? Right? So here we can see it's 32 QV stands for quantum volume. So this one is 32 QV. Then down here, we have a 15 qubit device that's only 8 quantum volume, right? So it seems a little bit weird. Here we have a 5 qubit device that's 8 quantum volume, et cetera, et cetera. Now, quantum volume is a metric that IBM developed to try and come up with a uniform and sort of consistent way of measuring the power of a quantum computer. Now, power is subjective, obviously, and different companies like Google came up with their own different measure. IBM's is called quantum volume. There's a number of others that are used in the research literature. I won't go into how to calculate it, but the basic idea is it's supposed to be a sort of holistic, comprehensive measure of how powerful a computer is. Now, the classic example for this is D-Wave, which is another quantum computing company. They make computers that have thousands of qubits, right? Like if you go on D-Wave's website, you'll see like a 5,000 qubit quantum computer being advertised. And a lot of people are confused by this because they're like, well, hold on a minute. Like if you ran Shor's algorithm with 5,000 qubits, wouldn't that break encryption? Like wouldn't all of our websites be broken right now? And I don't actually know how many qubits it would take to run Shor's algorithm and break anything that we're using today. But the thing to understand there is that D-Wave's quantum computers, for various reasons, all of their qubits individually are not as powerful as the qubits that we're learning about. So when we talk about a qubit, we are essentially talking about the maximally powerful, theoretically perfect qubit, right? And for something like Shor's algorithm, that's what they assume. They assume that you have theoretically perfect, maximally powerful qubits. On some machines, though, there's a trade-off, right? They can build more qubits into the quantum computer, but the trade-off is that those qubits individually are going to be less powerful for a variety of reasons. So quantum volume and other measurements of quantum computational power are meant to sort of capture those differences, because just looking at the number of qubits is not a very reliable measure of how powerful a quantum computer actually is. So that's what you're seeing here, is just measures of the power in some sense. Exactly how you define that is beyond my knowledge and beyond the scope of this course. Okay, so I think that is all I was going to go over, except for the actual optional content. So I'm going to dive into that. And for that, I'm going to revisit one of the job that I ran on the real quantum computer here. So I just want to come back to this idea that our results were imperfect, right? So not only did we have, non-50-50 probabilities because there's some randomness, right? We also saw these states appearing. And that's something we did not get in the simulator, right? Even though the simulator sort of metaphorically flips 1,024 coins, it doesn't get exactly 50-50 either, because there's some probabilistic nature in quantum computing. The simulator at least didn't get any wrong answers. Here with the real quantum computer, we actually got totally wrong answers in about 2% of cases. The reason for that, as I said, is noise and errors in the quantum computer itself. And that's what we're going to talk about in the optional content. So I'm going to go ahead and switch back to my tablet. There's been a lot of switching around today. That's okay. All right. So just to drive this point home a little bit more, these are some experimental results from one of the other TAs, Aman, that show a little bit more of sort of how the noise of quantum computers can be pretty bad, actually. So just to quickly explain what's going on here, the purple line, which is the same in all of these diagrams, is our target. So I'm not going to show you the quantum circuit for this, but there's some quantum circuit that has been constructed, and it's supposed to give you a probability distribution that looks like this, right? So it should be high on the two edges, and then it should have a peak in the middle. All of the other lines are actual data from running this circuit on actual quantum computers, right? So you can see here, we've run it on the Melbourne machine, the Valencia machine, and the Yorktown machine. So those are just 3 of the possible quantum computers you could pick. And all of them give, not perfect results, to say the least, right? So for example, the best performing one is Valencia. And here you can see it's this green line, by the way. Now the Valencia machine follows roughly the same pattern, right? But it's not quite reaching as high of a probability as we would want in some of these cases. That's okay. But you can see for Valencia and Yorktown, like this peak in the middle is almost barely distinguishable, right? It's quite low. There's a lot of noise, and it's honestly, it's difficult to pull any trends out of this. Now, this is the circuit being run with 4 qubits. That's what the n equals 4 means up there. If we try running it with 5 or even 6 qubits, you can see the results get dramatically worse, right? Up to over here, where we basically have no signal at all. There is no trace of the pattern we were trying to go for. So this is, I'm not exactly sure when this was run, but it's certainly within the past couple of years. So things have improved since then, for sure, but we still are a far ways away from theoretically perfect or even anywhere close to perfect quantum computers. Now, I want to talk a little bit about this error, the nature of it, how we might fix it, and where it comes from. So there's a couple of sources of error and noise in quantum computers. I'll talk about 2 of the main ones here. There's probably more, but I like to think of them in 2 general categories. The first one is that you're going to have some sources of error from imperfect instruments. So by instruments here, I just mean like things in your lab, right? So for example, maybe you can't measure an electric field super precisely, right? Some of your measurement devices will have margins of error, and of course you can't measure it precisely. So measurement might be uncertain. Another potential source of error, though, is the gates themselves, right? So I've talked about the idea of using laser pulses to do gates. Well, it might be that, for an X gate, you know that you have to shine the laser for exactly 11 milliseconds at exactly 512 hertz of frequency, right? Well, our laser devices might not be that precise, right? Maybe it shines it for 11.2 milliseconds, and maybe the actual frequency is 514 hertz instead. So all of those little differences with how our lasers behave will also influence the ultimate operation. It'll mean that we don't quite do an X gate, right? And if you have more gates in a row, it'll just get more and more, you'll get more and more error as you go through the circuit. So what did I say here? You can't do the gates precisely. And then the last one here is just environmental factors. So you've probably heard that a lot of different quantum computers need to be supercooled, right? Now, we have pretty good technology to supercool things down to ludicrously low temperatures, which is really cool, but we're never going to get things down to literal absolute zero, right? And for example, even the research that I'm doing right now, our quantum computer is very sensitive to magnetic noise. So all I mean by that is if you have rogue magnetic signals coming into the quantum computer, that will throw off your measurements quite a bit. So we have to be aware of how the Earth's magnetic field changes. We have to be aware of how MRI clinics in the same city are using their machines, because our computer will pick up very small changes in the magnetic field around it. So generally speaking, your environment is noisy, whether that's temperature or magnetic field or anything else. You're not going to have a perfectly controlled ideal environment. And so all of these things are going to just lead to noise and imperfections in your computation. The second category is what I'll call physical error. And this is just meant to reflect that some quantum systems, inherent in them is some error. So I'll give you one example. A couple of labs ago, we talked about the levels of electrons, right? We showed some pictures of electron orbitals, and we said that one way to do quantum computing was to treat, for example, the s orbital as ket 0 and the p orbital as ket 1. And so if I were to draw that in the classical inaccurate way, you have your nucleus right here. And maybe if our electron is close to the nucleus, that's going to be ket 0. And if our electron is far from the nucleus, that's going to be ket 1. And then we can do our computations by exciting the electron to a further out energy state, or letting it decay back onto the inside of the atom. Now, in this case, well, I kind of gave away the answer when I said that. If we excite something up to the 1 state, it could be that that state is unstable, right? And so there will be some decay over time where the electron comes back to the 0 state. So even if we had a perfect environment with perfect measurement tools and perfect gates and everything, right? So even if all of these factors up here did not apply, we would still see that over time, our 1s would gradually turn into 0s just because of the nature of the system. So this starts to touch on something called decoherence time, which you might have heard of. And it basically refers to the time it takes for any given quantum hardware to decay to a state where you cannot do anything with it anymore, right? And so this electron example is a great example of that, where we can excite electrons to be really, really energetic, but over time, they lose some of that energy, even if we don't touch them, right? So we have to do something to actively try and keep them energized. Otherwise, they will naturally fall back to the 0 state. And there's similar kinds of ideas in other quantum platforms as well. Okay, so a little bit on how we can catch errors then. Now, I'm going to dip a little bit into classical computing here to talk about this, because as somebody asked, the reason classical computers have very few errors anyway. Remember, classical computers do sometimes have errors, right? Every now and then your computer will crash or something won't work for some unexplained reason. But the error rate on classical computers is very, very, very low, right? And the reason for that is because of something called error correction. So suppose I start with 1, 0, 1, 1, right? So suppose I have 4 wires that are supposed to be 1, 0, 1, 1. Now, let's say that I do a meaningless circuit, right? So I'm just going to pass each of these through 2 NOT gates. So remember this little triangle with the circle on it just means a NOT gate. I'm going to do 2 NOT gates on each of these bits. Now, my question to you is, okay, what should the output be here? So for this first line, we start off in a 1. We're going to flip to 0, and then we should flip back to 1 again. And you can do the same thing for all of these, and we should end up with 1, 0, 1, 1 at the end, exactly. But in real life, right, for all of the reasons I just described, there's a chance that things go wrong in the middle here, right? Either our wires aren't quite perfect, or maybe we measure the wrong thing at the end, or maybe our gates don't quite work as we expect. And let's just say that there's a 5% chance of our gates flipping, or sorry, of our bits flipping. So in that case, you might end up with a result that looks like this. With such a simple circuit, we can clearly see that this is an error. But if your circuit is massive, it might not be very obvious that an error has occurred. So the question then becomes, is there an easy way to fix such an error? Now, this is starting to get into the realm of error correction, which is a huge and honestly super interesting and cool area of research right now. And it's basically the study of, given an imperfect system, how do we try and come up with perfect calculations? The simplest example of error correction is something called majority rule. So what you do in this is you just create multiple copies of your circuit and run all of them. So here, let's say I do majority rule with 3 copies. I would create 3 copies of my circuit. Right, and I won't go through and draw all of this, but just pretend that all of these have the same double NOT gates in the middle. And then I will go ahead and measure what happens at the output. So let's suppose that nothing goes wrong in the first 2 circuits, but something does go wrong in this last circuit. So notice here, my 0 is incorrect, right? Now, without knowing that an error has happened in the circuit, I can just look at these 3 results. I see, okay, I got 1, 0, 1, 1, I got 1, 0, 1, 1, and I got 0, 0, 1, 1. And what majority rule tells us is just take whatever the majority says. So here, the majority says that the answer should be 1, 0, 1, 1. And so that's what we'll take as our answer, and we'll just throw this one out. Now, of course, this is not foolproof, right? You could end up with a terrible situation where 2 of your circuits fail and you get the wrong answer. But this at least improves your chances, right? Without going through the exact math, hopefully you can sort of see that even though there's a 5% chance of each of these circuits individually failing, there's a much smaller chance that more than one of them will fail at once. So this is how you typically do error correction, or like some variety of this. There's more complicated schemes as well, for sure. But this is the general idea, right? You make some copies, or you introduce some redundancy of your data. And then at the end, you have some way to figure out what the correct answer was based on that redundant data. Okay, that's the world of classical computing. What about quantum computing? So we'll do sort of a similar example, right? Suppose I start with ket 1, 0, 1, 1. And then I'm going to feed each of those through 2 X gates. So again, what should happen here is the X gates should undo each other. And so at the end of the circuit, we expect to get the exact same result. We expect to get 1, 0, 1, 1 as our result. But just like before, let's say that each qubit has a 5% chance of flipping. And so we might get something that's not the correct answer on the other side. Again, I would ask the question, how do we fix such an error? And again, there's many different answers, but one way you can do it is the exact same strategy. So actually, in this case, it turns out that knowing some classical computing can help you with quantum computing, because we can do the exact same thing. We can start off with 3 copies of our initial state. We can run all of them through the same circuit, and then we can take what the majority says at the end. And that will also fix our error. There's only one problem with that. And this is my last slide. I know this was a bit of a longer optional content, but I want to talk a little bit about why quantum error correction is quite a bit harder than classical error correction. And the basic idea, at least as far as I understand it, is that qubits don't just have to flip, right? In all of my previous examples, I was saying, oh, well, if there's a 5% chance that things flipped, then what would happen? But of course, qubits don't have to flip. If you think about it on the block sphere, the meaning of a flip, that type of error, is a 180-degree rotation around the x-axis, right? But what if we don't do a 180-degree rotation? What if we did like a 90-degree rotation, right? Or we haven't even talked about phi. What if phi changes? Is there an easy way to detect and correct all of these different changes? And the answer there is not really. Quantum error correction codes tend to be quite complicated because there's so many different types of errors that can happen. In classical computing, because you just have 1 and 0, it's pretty straightforward, right? Either your bit stays the same or it doesn't. And that's the only type of error you have to think about. In quantum computing, though, because you have superpositions, because you have entanglement, you have phases, there's so much more that can go wrong. It's much, much, much more difficult to correct for all of these types of errors at once. So usually you will look at whatever hardware you're using, you'll try and figure out what the dominant sources of error are. So maybe in maybe in IBM's machine, phi doesn't tend to change very much. So we're going to mostly ignore that, and we're going to focus on how to fix errors in theta, right? That's one possibility. But even then, it's still harder because theta could change by any number of degrees, and you need some way of figuring out what went wrong. So all of that to say, quantum error correction, very fascinating, very difficult. And it is still an active area of research today. So I hope that brief introduction was interesting. Does anybody have questions about any of that stuff? Full disclosure, I'm not a quantum error correction researcher, but I know a little bit about it. So one person says, does having more shots help to fix errors in quantum systems? It can, yeah. The way that we normally think about it, though, is that shots are a way to get closer to an accurate prediction of what your superposition was, right? So even if we forget about errors for a minute, if my output state was this, how do I tell the difference between that state and, let's do well, here, let me draw this a bit more explicitly. The state that we had was, 50 over 100. So 1/2 chance of ket 0 plus 1/2 chance of ket 1, right? We know that that should have been the answer. But if we don't know what the answer should be, which, obviously, usually when you're doing a computation, you don't know what you're expecting. That's why you're doing the computation in the first place. How do we know that it wasn't, 51 over 100 ket 0 plus 49 over 100 ket 1? Right? These two states are pretty similar, right? The probabilities, if you flipped a coin and the coin had a 51% chance of landing on heads, it's going to take you more flips to figure that out. So usually when we talk about increasing the number of shots, it's to distinguish between states like this, states that have very similar probabilities, but maybe you want to tease out a bit of a difference, then you need to use more shots to make sure of what you're seeing. Is what I'm saying right now related to the law of large numbers and probability? Yes, exactly. It is the law of large numbers. Okay, so I guess coming back to the question here, though, does the number of shots fix errors? It kind of depends on how you look at it, but usually the way that people think about it is actually no, right? Because remember, when you measure a quantum system, it collapses. And so for every single one of these shots that we're talking about, we have to recreate our initial state, we have to redo all of the gates, and we have to redo our measurement. And so for every one of those, say 1,024 shots, you could have errors introduced, right? And so there's kind of two different kinds of uncertainty here. There's uncertainty coming from errors and noise, but there's also uncertainty coming from the probabilistic nature of quantum mechanics. And so through some combination of error correction and using more shots, you can try to mitigate one or both of those. But ultimately, they can both be an issue when you're trying to run experiments. Okay. How does Shor's algorithm correct for errors? So Shor's algorithm does not. Shor's algorithm assumes you have a perfect error-free quantum computer. So you would have to apply some error correction code on top of it to make it work with a real quantum computer. And that's one of the reasons that, so the keys that we use to secure online communications today is like 2048 bits, for example, right? If you look at If you look at your browser, you'll be able to see that there's, a 2048-bit key that is securing your internet session with your bank, for example. In order to crack that, you would roughly need about 2048 qubits, which doesn't sound like too bad, right? Because today we already have 50 qubit devices. We only have to go 10 to 20 times larger than that before we can start breaking the internet. No, not quite, right? Because the 2048 is assuming that you have 2048 perfect qubits. We're still a long way away from that. So instead, what you'd have to do is you'd have to have one of these things where you do like 3 copies of the experiment, right? For example. So then you would need 3 times 2048 qubits to do that. And for other quantum error correction schemes, the overhead gets much larger, right? Instead of being 3 times as many qubits, you might need 10 times as many qubits for some of the really good error correcting codes. So that's why, like for Shor's algorithm, you're probably going to need many more than just 2,000 qubits to do it properly. It's because of error correction, because you need to apply these codes that do several copies or maybe many, many copies of the same thing multiple times. Okay. Can anyone recommend a book for this course? So I believe, let me think. There was actually a project like internally at Qubit by Qubit to develop a textbook. I don't actually know exactly where that's going. There are some great resources, like textbooks that you can read on quantum computing in general. There was a resource sheet sent out over the winter break, which I will also find a link for and include in my announcement, that has a whole bunch of different resources, and it describes what level of knowledge they're for as well. So if you're a university student, or if you're a high school student, or if you're a working professional, we have different recommendations based on your skill level. So I will also make sure to send a link to that. Okay, so one person asks, wouldn't taking the average be more efficient than taking the mode of values? Yeah, so in my majority rule example, we were effectively taking the mode, right? If you're familiar with these terms from statistics, we're effectively taking the mode of our measurement. You could do this other ways. You could take the median, you could take the average. There are other different codes. This is just the simplest one, and it sort of captures the main ideas. Okay, so somebody asked something about the Q sphere. I'm going to suggest if you have more specific questions about the IBM Q experience, at this point, I'll recommend that you just go on Piazza, screenshot your issue or like the circuit that is behaving differently than you expect, and post it on there. We should be able to help explain for your specific case. Oh yeah, somebody already linked in the chat that resources page that I was talking about. I will also include that though when I send out my announcement. Okay. Is there anything else? Can't we somehow connect 4 quantum computers and make a 2,000 qubit working quantum computer and run Shor's algorithm? Not exactly. So the copying mechanism that I explained here for majority rule, like I said, is the simplest case. Other error correcting codes are not just 3 independent circuits working on their own. A lot of times they have interaction between them to try and improve the error correction. So you would actually need 10,000 qubits on the same computer to properly run those algorithms. For career, the person asking about career prospects, I touched on that just very briefly a couple of minutes ago. But I think the other resource that I would direct you to is that panel conversation that we had earlier in the year. And I will link to that in my announcement that I send out after the lab. So somebody says the quantum no cloning principle means that a simple majority rule error correction can't be implemented on quantum computers. Fair point, but I guess all I'll say here is I'm not suggesting that we actually clone these states. We're assuming that we know how to construct 1011. And so just as easily, we can construct 3 copies of it. You're right that you can't clone an arbitrary quantum state, But if you know what the quantum state should be, then you can produce copies of it. Hopefully that distinction is clear. Okay, so I think that brings us to the end of the questions. Okay, one person says, can I add 1 + 1 with the gates that we have? Yeah, yes, you can. So you can look up how, so usually people wouldn't, do an adder. It's called an adder, by the way, like a circuit that does addition. Usually people wouldn't do an adder on a quantum computer. Maybe you'll find something if you Google. But my recommendation actually would be to look up how to do an adder with a classical circuit. And you'll see that it just uses gates like, like a NOT gate or an OR gate. And you can try to think about how to implement those things on a quantum computer as well. Okay, so I think I'll wrap things up there. Thank you to everybody who stayed out right until the end. As usual, this is all going to be recorded. And again, because I had a pretty long and rambly optional section, I'll make sure to add chapter markers in the recording so you can go back and watch just one particular part if you would like. Other than that, good luck with the homework. Be sure to check up on Piazza with any questions, and I will see you all next week. Bye.